Hello my dear wonderful genius students, I'm back again with a new video. This is lecture number 18 on complex analysis, and today's topic of discussion is applications of Cauchy's integral formula. Students, in this video I'm going to solve total 5 problems by using Cauchy's integral formula. So without wasting time, let's get started. Problem number 1. Evaluate this integral where C is the circle modulus of z minus a equal to r. So according to this problem, the radius of the circle is small r and the center is located at the point z equal to a. So first let us calculate the singular point or pole of this integrand. The poles or singular points are given by putting the denominator equal to 0, that is z minus a equal to 0. This implies z equal to a. So here we have seen that the pole or the singular point is located at the center of the given circle. So this is the location of the pole. The pole at z equal to a lies inside the given circle modulus of z minus a equal to r. Since there is at least one pole or singular point within this circle, so therefore we can apply the Cauchy's integral formula, which is f of a equal to 1 by twice pi I integration along closed curve C f of z divided by z minus a into dz. After rearranging, we can write integration along closed curve C f of z divided by z minus a into dz equal to twice pi I into f of a. So first let us calculate the value of f of a from this integral. So according to this problem, f of z equal to 1. So therefore f of a is also equal to 1. Now apply Cauchy's integral formula. So by Cauchy's integral formula, integration along curve C dz divided by z minus a is equal to twice pi I into f of a, whose value is 1. So after multiplying, we will get twice pi I, which is the answer. Now let us solve the second problem. According to this problem, we have to evaluate this integral where C is the circle modulus of z minus 2 equal to half. So according to this problem, the radius of the circle is half and the center is located at the point z equal to 2. First, let us calculate the singular points or poles of this integrand. We know the poles or singular points can be obtained by putting the denominator equal to 0. So that is z square minus 3z plus 2 is equal to 0. So we can write z square minus twice z minus z plus 2 equal to 0. First let us take z as common from these two terms, z minus 2. Next, from these two terms, let us take minus 1 as common. So we will get this one. Now let us take common z minus 2 from these two terms. So we will get z minus 2 into z minus 1 equal to 0. So therefore, the values of z are 1 and 2. So we have seen that there are two poles for this integrand, which are z equal to 1 and z equal to 2. So therefore, the poles are z equal to 1 and z equal to 2. The location of these poles are at this position and at this position. Again, we have seen that out of these two poles, only one pole at z equal to 2 lies inside the given circle. So we will apply Cauchy's integral formula for this pole only. Let me write these points. Out of two poles, only one pole at z equal to 2 lies inside the given circle. Modulus of z minus 2 equal to half. So therefore, by Cauchy's integral formula, integration along curve C, z divided by z square minus 3z plus 2 into dz is equal to integration along curve C, z divided by this part. This part can be written as z minus 2 into z minus 1 dz. Now let us rearrange this term. So after rearranging, we will get integration along curve C, z divided by z minus 1 divided by z minus 2 into dz. Now let us calculate the value of the function f of z at the singular point z equal to 2. So according to this problem, f of z equal to z divided by z minus 1. So here f of z is equal to z divided by z minus 1. So therefore, value of the function at z equal to 2 will be equal to 2 divided by 2 minus 1, which is equal to 2. Now apply Cauchy's integral formula for this integral. So therefore, integration along closed curve C, z divided by z square minus 3z plus 2 into dz is equal to twice pi iota into value of the function at the singular point z equal to 2 is equal to twice pi iota. We know the value of the function at the singular point z equal to 2 is 2. So into 2. So after simplifying, we will get 4 pi iota, which is the answer. Next, let us solve the problem number 3. According to this problem, we have to evaluate this integral where C is the circle modulus of z minus 1 equal to 2. So according to this problem, the radius of the circle is 2 and the center is located at the point z equal to 1. So first, let us find out the singular points or poles for this integrand. We know the poles or singular points can be obtained by putting the denominator equal to 0, that is z minus 1 into z minus 2 equal to 0. This implies z equal to 1 and 2. So we have seen that for this integrand we have two poles z equal to 1 and z equal to 2. So therefore, the poles are z equal to 1 and z equal to 2. The poles z equal to 1 and z equal to 2 are located at this position and at this position. Here we have seen that both the poles z equal to 1 and z equal to 2 lie inside the given circle modulus of z minus 1 equal to 2. So, we will apply Cauchy's integral formula for z equal to 1 and for z equal to 2 separately. First, let me write these points here. Both the poles at z equal to 1 and at z equal to 2 lie inside the given circle modulus of z minus 1 equal to 2. Therefore, by Cauchy's integral formula, by Cauchy's integral formula, integration along curve C, z square plus 2 divided by z minus 1 into z minus 2 into dz. This part can be written as integration along curve C1 z square plus 2 divided by z minus 1 divided by z minus 2 into dz plus integration along curve C2 z square plus 2 divided by z minus 2 divided by z minus 1 into dz. First, apply Cauchy's integral formula for this integral. So, for this integral, f of z equal to this one, twice pi I z square plus 2 divided by z minus 1 at z equal to 2. Next, apply Cauchy's integral formula for this integral, whose value is twice pi I z square plus 1 divided by z minus 2 at z equal to 1. Now, let us simplify this term and this term. So, we will get twice pi iota into, if we put z equal to 2, then we will get 6 plus twice pi iota. Again, let us put z equal to 1 here. After simplifying, we will get minus 3. So, finally, after simplifying, we will get 6 pi iota, which is the answer. Now, let us solve the problem number 4. According to this problem, we have to evaluate this integral where C is the circle modulus of z equal to 2. So, according to this problem, the radius of the circle is 2 and the center is located at the origin. Now, let us evaluate this integral. We can write this integral in the following form: integration along curve C tan z dz is equal to integration along curve C sin z divided by cos z into dz. Our next target is to find out the singular points or poles. The poles or singular points are given by putting the denominator equal to 0, 0, that is cos z is equal to 0. If we simplify, we will get z equal to minus pi by 2 plus pi by 2 3 pi by 2 comma dot dot dot. So we have seen that this integrand has infinite number of poles. Out of infinite number of poles, only 2 poles at z equal to minus pi by 2 and at pi by 2 lie inside the given circle modulus of z equal to 2. So therefore, we will apply Cauchy's integral formula for z equal to minus pi by 2 and for z equal to pi by 2. First, let me write these points. Only 2 poles at z equal to minus pi by 2 and at z equal to pi by 2 lie inside the given circle modulus of z equal to 2. So therefore, by Cauchy's integral formula, we have integration along curve C tan z dz is equal to integration along curve C1 sin z divided by cos z into dz plus integration along curve C2 sin z divided by cos z into dz. Now apply Cauchy's integral formula for this integrand first. So after applying Cauchy's integral formula, we will get twice pi I into sin z at z equal to minus pi by 2. Again, let us apply Cauchy's integral formula for this integral. So finally, we will get twice pi I sin z at z equal to pi by 2. We know sin minus pi by 2 value is minus 1 and sin pi by 2 value is plus 1. So we will get twice pi I into minus 1 plus twice pi I into plus 1. So after simplifying, we will get 0, which is the answer. Now let us solve the last problem. According to this problem, we have to evaluate this integral where C is the circle modulus of z equal to 3. So according to this problem, the radius of the circle is 3 and the center is located at the origin. So first, let us calculate the singular points or poles for this integrand. We know the singular points or poles can be obtained by putting the denominator equal to 0. That means z plus 1 whole to the power 4 equal to 0. So therefore, we get z equal to minus 1. Here z equal to minus 1 is a pole of order 4. Here z equal to minus 1 is a pole of order 4 which lies inside the given circle modulus of z equal to 3. Now let us apply Cauchy's integral formula for nth derivative of an analytic function, which is integration along curve C f of z divided by z minus a whole to the power n plus 1 dz is equal to twice pi I divided by n factorial into f to the power n a. For our case, n equal to 3. Therefore, by Cauchy's integral formula for nth derivative of an analytic function. We have integration along curve C e to the power twice z divided by z plus 1 whole to the power 4 dz. This 4 can be written as 3 plus 1. So, here n equal to 3 is equal to twice pi iota divided by 3 factorial into d cube divided by dz cube into e to the power twice z at z equal to minus 1. So, after simplifying, we will get twice pi iota divided by 3 factorial means 6. After simplifying this part, we will get 8 into e to the power twice z, where z equal to minus 1. After substituting z equal to minus 1 here, and after simplifying, we will get 8 pi iota divided by 3 e square, which is the answer. With this, I have completed the module number 2. From next video, I will be starting the contents of module number 3. Okay?